Okay, you should have out in Lecture 10 notes. Why is the standard deviation such a powerful measure of data spread? And the answer can be seen in the following picture. This is true, this is typical of many data sets, true of many populations of data, especially those that have kind of a bell-shaped curve to how they are distributed on the real number line, like we've already seen with some histograms. So what we often find is the following. So if I think of just having all the data points strung out along the number line, somewhere on this number line will be the mean mu, okay? Well, what we find is that if we then compute sigma, we compute mu and we get this value, we compute sigma and we get some positive number. If I were to move up the number line a distance sigma and down a number line a distance sigma, so this right here would be mu plus sigma and this would be mu minus sigma. Maybe I'll stick that in. Well, actually, I don't think I will. I'm going to get too crowded here. But I go up and down a distance sigma off of mu, and that interval that I get, which I can write it right here. I can say it's mu minus sigma up to mu plus sigma. This is about 68% of the data in a typical data set, all right? If I go up another distance sigma, another step sigma, and down another step sigma, then what do I have here? If I can, hope you have enough room in your notes to write all this. This is really the interval mu minus 2 sigma up to mu plus 2 sigma. And it gives me about 95% of the data in the data set, typically. Let me go up one more. So I can just put it right here. This is mu plus 3 sigma, and this is mu minus 3 sigma, and that will typically give me, gosh, I've forgotten off the top of my head, over 99, greater than 99% of the data. Again, that's pretty typical for many populations of data. So you can see that I can use sigma to get some kind of an idea how spread apart the data are. And in fact, you can see that small sigma means the data are clustered near mu. Large sigma means the data are spread apart from mu. If sigma is 0.0001, then off of mu, I just have to go a little distance either way to get 68% of all the data, a little bit more to get 95%, right? But if sigma is, 10,000, then I got to reach really far in each direction to get 68% of the data, and then double that again in each direction to get 95% of the data. So a big sigma means the data are all spread along the number line, and a small sigma means they're all clustered in very close. All right, I think, so I guess I make a note here that the above, meaning this number line up here system, is also true in general for fairly large, well-chosen samples. And of course, you just replace mu with x bar above and sigma with s. I'm not going to draw that in. You can write that all in with your notes, but you should have something very similar for a large data set if it's a well-chosen data set. We'll talk more about what well-chosen means soon enough. Okay, well, we are still looking at then having ways of describing data sets, right? You can see that these two numbers, mu giving me kind of a center and sigma giving me kind of an idea of the spread of the data, give me a good picture of a data set. Just those two numbers can tell me a lot about a very large data set. We're going to look at one thing right now that allows us to compare data values in a data set and even data values across data sets. And this is just a natural time to do that. I want to talk about the z-score of a data point, or really of a data value. And the z-score is defined to be, if x is the data value, its z-score is, I take x and I subtract away the mean. So that tells me how far I am away from the mean, but then I will divide by the standard deviation. And so what I end up with is the numerator tells me how far apart that data value is from the mean, and if it's bigger than the mean, that'll be positive. If it's less, then it'll be negative. But then if I divide by sigma, what I really end up with is in a sense, how many steps of size sigma this data value is away from the mean. All right? And we'll look at some examples here. In fact, yeah, let's do that right now. Example. Suppose for a population, mu is 120 and sigma is 15. Okay. Let's find the z-score for the data value x equal 145. Okay. The answer is, why don't you pause me and see if you can compute it. It's just sticking everything in that formula, seeing what you come up with. All right, I shall do it. I take the data value, x, 145, minus mu, which is 120, and divide by sigma, which is 15. If I do that, I get 25/15. I get 5/3, right, which is 1 2/3, 5/3, which is 1.6, where the 6 repeats forever and ever. So I could round it to 1.67 for the nearest hundredth, all right? So 1 2/3. All right, so 145 is 1 2/3 steps larger than 120 if the step size is the standard deviation 15. Try this one. Let's keep everything the same except find the z-score for 45. Okay, so x is 45. Give that a try. All right, we get 45 minus 120 divided by 15, which I believe works out to be, -5. Works out to be, I think, -5. I get -75 on top, divided by 15 is -5. So this tells me that this data value 45 is 5 steps to the left below the mean, where each step size is the size of the standard deviation sigma. Okay, a very famous statistician, R.A. Fisher, just kind of declared one day that an event should be called unusual, if you read down here in your notes, if it has a less than 5% chance of occurring. So what do we mean by a less than 5% chance? Well, we're talking about probabilities there, which again, we haven't really talked about formally yet, but you can get the idea in that if it's a very rare sort of a data value, that would have a low probability. If it's a more common data value, it would have a high probability. So if I'm looking here at the data, spread of the data in a population, I see that I get 95% of my data between 2 sigmas below mu and 2 sigmas above mu. So if an event has a less than 5% chance of occurring, we might connect that with the idea of having this leftover 5% of the data being out here in the tails, right? So beyond 2 sigma in this direction or beyond 2 sigma in that direction, if a data value falls in there, we would consider it by this criterion being unusual. So the z-score would be, well, I just basically told you, I'm going to put this in quotes because later on we will more formally define what we mean by unusual, and it won't be exactly this definition, but this is a common definition that is used. So unusual data points have z-scores. Well, it's got to be beyond 2 sigma beyond mu, so it has to have a z-score. If I compute my z-score, it will be 2 steps, beyond 2 steps of size standard deviation beyond the mean, right? So it will be a z-score greater than 2 for unusually large or less than -2 for unusually small. If my z-score is bigger than 2, I'm going to say my data value is unusually far away from the mean. If it's less than -2, it's unusually far away from the mean in the other direction. Let's do quick example here. Okay, so we have the population of adult male hippos has mean 3,500 pounds and sigma 300 pounds. Find the z-score of a male hippo with weight 2,800 pounds. So why don't you try that? X equals 2,800. I want the z-score. All right, so pause me and give that a try. Okay, I get 2,800 minus 3,500 divided by 300. Correct? And that works out to be, I think, -7/3, which is -2.33333 forever. All right, that's less than -2. So this hippo is unusually light, unusually small, right? A mere 1 ton, 800 pounds. For the second one, we have a 4,000-pound hippo. Certainly bigger than the mean. Is that so big that we would think it's unusually mean? So pause and find the z-score. Okay, I get, do it right here. Z-score is 4,000 minus 3,500 over 300, which works out to be positive 1.6. Repeating, I think it works out to be 5/3. So that is less than 2, right? It's a positive z-score. It's big, but it's less than 2. So this is less than 2 standard deviations bigger than the mean. So by this criterion, it's not unusually heavy. Okay. And it says here that, yeah, what are the cutoff weights for unusually heavy and unusually light hippos? And the cutoff weights, that's easy to figure out, right? Cutoff weights. I want to do the the lower one. Let's do that's mu minus 2 sigma, which is 3,500 minus 2 times 300, and you get 2,900 pounds. And that's the lower one, and the upper one is mu plus 2 times sigma. That's 3,500 plus 2 times 300, and that works out to be 4,100 pounds. There are the 2 cutoff values, and so what we're really saying is if you fall outside that, you're either unnaturally heavy or unnaturally light for a hippo. And we're also saying that, look, this 2,900, that corresponds to what, this value right here. And the 4,100 corresponds to this value right here. So 95% of adult male hippos are going to weigh between there and there. That tells you something about the data set for all the weights of hippos, right? They're between 2,900 and 4,100 pounds. Okay, last example. The really kind of the neat thing about, one of the neat things about z-scores is it allows us to compare how unusual data values are even in different data sets. Excuse me. So if you read this example here, Wally scored 1240 on the Ubwat, and Wanda only scored 46 on the Ubway. So Wanda's score is a lot lower than Wally's, right? Does that mean Wanda doesn't know as much about underwater basket weaving as Wally? And the answer is not necessarily, because the exams have totally different scales. So what you want to do is you want to look at just how unusually high or maybe low Wally's score is versus Wanda's, relative to the data sets they came from, relative to the populations they came from, and then you can compare. I'm not going to say any more. I'm going to just ask you to pause and work this out and see what you come up with, and then I'm just going to give you the answer because we're about out of time and out of space. Okay, Wally's Z-score. You should see that it is, I think, 1.2. So he is 1.2 standard deviations above the mean. So he's better than average. Wanda's Z-score. You work that out, and you should get that it is 2. So she's 2 standard deviations above the mean. So it looks like Wanda probably knows a little more than Wally, even though her raw score is a lot lower because it's a totally different exam. But by comparing Z-scores, we can actually compare those data values.